Okay, good morning, and I'm very pleased to be here to talk to you a little bit about network time security. Just a little bit of background about myself. I've been working for the Internet Society now for about 10 years, and even prior to that, I've been working in the IETF on the network time protocol and time synchronization in general. And I currently chair the IETF working group on NTP and the IEEE 1588 subcommittee on security. So what I wanted to talk a little bit today was about time. Humans have always measured time. It's important in a number of ways. And it's vitally important to a number of our systems, and it's a key part of our infrastructure, but often it is an overlooked part of our infrastructure. In that there's a small community of people that work on this in this space. Some of the areas where time is very important is like maintaining synchronization in power grids, actually your web security and the time stamps and certificates require quality time synchronization. Synchronization of transportation systems, the stock markets, and even the original navigation problem was solved actually with time as opposed to navigation. So where does accurate time come from? There's a very basic architecture that you can think in terms of, in that you have a time reference. A lot of nations have their own time references, and all of these time references are coordinated to UTC. So for example, in the United States, there's the UTC USNO, so that's a time source that's traceable to. And then this time is disseminated in a number of ways. The most common way is through something like a global navigation satellite system, like Galileo or GPS. And then it is distributed and synchronized through computer networks using NTP and PTP, which is what most of you all would already be familiar with. The network time protocol developed by the IETF has been around for over 30 years and is pretty much comes installed by default in a lot of applications and platforms. And the precise time protocol has been developed by IEEE specifically for higher precision and for hardware time stamping. So there are these two basic protocols. They both exchange time over a network, a computer network, for the purposes of clock synchronization. And then they use the information that's exchanged to determine the offset between two independent clocks. And then based on that, they make alterations to one of those clocks. They use different techniques for forming these, but they form a hierarchical tree structure that's the basis for that time information. And there's a little bit of differences in the architecture of the two, but they are somewhat resilient in the presence of packet loss. The one thing about this is the time community has not prioritized security because time in and of itself is not a secret. It's information that the time of day is not a value that people have considered to be something that would be a threat that you would want to corrupt in any way. And in the 20 plus years that I've been looking at this, or monitoring the evolution of time work in various communities, it's never really been a high priority. And that's really changed in the last 4 or 5 years. And part of that is you see continuing interconnection and decentralization. And the more you decentralize something, the more that you need to focus on the synchronization of the pieces that you've now taken apart. We also have increasing evidence of the impact of inadequate security. We see a number of incidents on a regular basis, and we see the interdependence between our security systems and our time synchronization. And then also we have some additional legal and compliance requirements, and these are becoming more and more stringent. So as I mentioned, attacks are occurring. There's a number of documented accounts of this. Vulnerabilities have been, lots of vulnerabilities are being discovered. And what we've realized is that in the NTP world, there's sort of three sources of problems One is flaws in configuration and implementation. So these are things where the protocol is it's not the way the protocol itself is specified. It's the way it has been configured in a operational system, or it's a bug in the implementation. The second source of errors that you see, or the problems that you see, are weaknesses in the actual protocol itself. And then the third is, beyond the protocol itself, is lack of any adequate security mechanisms in the protocol. And despite all of this, it's been, here we say over 8 years, since there's been any sort of an updated specification for time synchronization security until this year. And there's been ongoing work in both IEEE and in the IETF for over 8 years in both communities, actually. And this year, it looks like both of the communities will release updated specifications specifically for time synchronization security. The IEEE effort is currently in the final editing process in the IEEE processes, and the NTS document is in the IETF editor's queue, RFC editor queue. So that's both excellent news. So now we have these emerging security mechanisms for both of these protocols. And in particular, if we look at the IETF, I mentioned the 3 areas of the problems that we have: flaws in the configuration and implementation. In last year, an NTP BCP was published. This BCP collected information from years and years of experience from the operator communities and specified additional information on how to configure NTP so that it would be less vulnerable. In the weaknesses in the protocol itself, we published an updated MAC for NTP, which deprecated God, I just lost the name of that one. It deprecated a crypto algorithm you shouldn't be using, and put a more recent version in its place. This is RFC 8573. Additional weaknesses in the protocol are being looked at in the possible specification of an NTP v5, and also some NTP client data minimization work. And then the third piece, which is really sort of the meat of what I wanted to talk about today, is this lack of adequate security mechanisms. And so we have network time security, which has been specified. So the network time security document has been evolving in the IETF now for several years. It's gone through many iterations. And as of March of this year, it has been approved by the IESG and is currently in the RFC editor queue. So it's not quite published. It doesn't have an RFC, but all of the technical changes to the document have been completed, and we're at the final publication stage. So, so what does NTS do for you? NTS, well, the original version of NTS, we rolled our own key exchange, and we did a bunch of custom things, and then the security community reviewed it and came back, and they were questioning why we would want to roll our own solutions. And so NTS is based on TLS. And so it uses TLS to exchange key material, and then it uses NTS extensions for NTPv4 to secure the protocol itself. So it provides integrity for the NTP packets. It provides unlinkability once NTP has been turned into an NTS session, and also provided that the client is using data minimization techniques. It does
2
provide.
minutes left, please.
Excuse me?
2 minutes left.
Oh, 2 minutes. Okay. Anyway, it provides a bunch of additional capabilities: key, authentication of server, and authorization of clients. Anyway, so at this point, it's really time to talk about deployment. And there are several building blocks to deployment. There's the technology and standards development, which we've got. We've got prototype and preliminary implementations. We've done some initial interoperability testing. And the rest of the steps are where we need to go next. We don't quite have open source, production quality open source. We're looking for commercial products. We need to develop tools and troubleshooting. We need to deploy some preliminary deployments. We need to take that and develop some best practices, and then move on to large-scale deployments. So we have an Internet Society time security project, and we've divided it up into 4 pieces. And we are looking to take us from that point of preliminary implementations through to guidance. So this year we'll be focusing a lot on setting up a distributed multi-party test bed, conducting some virtual test events, and developing some test and measurement tools. And then taking all of that in the subsequent years and creating lessons learned in BCPs. With that, it's time to act. We are looking for some potential collaborators in this work. We've already talked to a number of folks that are interested in working with us. And in particular, we're interested in network operators, developers, potential testbed participants, any time service providers in particular, any folks that are providing like national time services for their countries. If you're interested in working with us on a time security project, you can send me email, or you can follow us on the Internet Society webpage. And with that, are there any questions?
Thank you very much, Karen. Mariela, are there any questions for Karen? ¿Tenemos alguna pregunta?
Oh, and I meant to say, here's a few resources, just a couple links that might be useful. I forgot to say that, so.
Continúa, César Macarena.
Gracias, Macarena. Thank you very much, Karen. There is no questions, but it's for future reference or for question. May you share us an email?
Oh, yes. It's right there. It's O'Donoghue@isoc.org. So.
Thank you. Thank you.
You're welcome.